So quick look at today's agenda. And mostly a lot of today, or this next chunk is about structures. So I'm going to give a bit of a setup, and I'm not a structures person deep down, right? So I'm gonna give some background here and talk about what OpenVSP can do in structures. And again, it's really just sort of the setup man here, and then Brian Sandoz is going to come in between our breaks and really put this stuff through the paces. So I just wanted to give you guys that little bit of the arc, and then we'll come back and round out with the last few presentations of the workshop. So let me go ahead and we'll talk about this. So this is really, excuse me, an overview about the structures capability. There's too much stuff here to go through every screen and to dive in and click on every parameter and demo everything. So what I really want to do is give an idea of how to think about OpenVSP structures capability and let you know sort of how that goes across the board. So yeah, this is about the big ideas and to set things up, not the details. There are some bugs in this stuff. It's actually a lot better than when these slides were made. I fixed a bunch of those bugs, but there's still bugs in there. As Brandon said, the structures capability can be used productively. It's been used by Brian to really amazing extent, and also by James Joseph at NASA Ames to amazing extent. But there are things that are frustrating about it. So save often, and we're trying to make it better as we go. So there is a structures capability, and it's intended for conceptual design, structural layout. You access it by going to the analysis menu and then the structures submenu, and there's 3 options there. And mostly we'll talk about we'll talk about each of them, but in this particular block of time, we'll mostly talk about the first, the FEA structure. Structures and assemblies are defined parametrically. You can define your material properties, some boundary conditions. There's a very limited capability to apply loads. We'll generate a mesh and a FEM file, or we can output a step or an IGES CAD file of the structure. And we'll talk about all these things. First, it's worth talking about some definitions, just so that we all are speaking the same language as I go through this. So in my parlance today, an assembly is made out of one or more structures tied together with rigid links. We don't have a way to, in very fine detail, have the mesh of a wing connect node for node to the mesh of a fuselage, for example, but that mesh would be one structure and the fuselage would be another structure, and we would make an assembly by tying them together with some rigid links between them. An individual structure is defined by the skin of a single component that defines the outer skin, and then all the internal parts are defined as mostly planes, but as parts that are then trimmed by that outer skin. So we lay out ribs and spars, and they're trimmed by the OML of a wing. A part can be either what I'm going to call a full depth, 0 depth, or other. And I'll talk about what these are real quick in a moment. So the materials is what something's made of. Aluminum, titanium, steel, wood, carbon. We can either have material properties that are smeared to represent a laminate, a panel, or a beam, or it can just be direct material properties. We have support for isotropic or orthotropic materials. A property is assigned to an element, and it's a combination of the material and some dimension. So for shells, that means it's a thickness. And for beam elements, it's the type of the beam. Is it a box beam or tube or an I-beam? And then whatever its parameters are, its length or its height and width or its diameter, its thickness, or if it's a general beam, just its moments of inertia, its EIGJ distribution. So properties are a combination of materials and a dimension. Materials are just the raw metal. Okay. So the FEM model is built the way we do it, is made of shell and beam elements. We do not have any solid elements whatsoever. We do have quads or tris as choices. We'll talk more about that in a bit. And we can either generate low order or high order elements. So in Nastran, that means we write out either C quad 4s or C quad 8s, C tri 3s, C tri 6s, or C bars. and Calculix, which is an open source FEM solver, which uses the Abacus file format. We write either S4 or S8s for quads, S3 or S6s for triangles, and B32Rs for beams. So here's the kinds of structures that we can represent, right? Everything's done with either shell elements or beam elements. And so the shell elements can be used to represent the skin of the parts, or what we call full depth interior structures. So something like a rib or a spar. And by full depth, I mean it's essentially a solid sheet that goes from one end to the other. There's not a bunch of holes in it or rings in it. And so we can represent a lot of these things that way. We also have beam elements. And so those we're going to talk about as zero depth, because they're, right, geometrically they're just a line, but they can have properties of like thickness and height, like an I-beam or something. But geometrically they have zero depth. And so you can use those to represent things like spar caps or stiffeners, stringers, or certain bulkheads if the depth of that bulkhead is not huge, or like this former over here. So we can represent the bulkhead as a full depth structure, and this former we would represent as beam elements running around the ring. Now there are things that we cannot really represent. We can't at this point represent what I would call partial depth structures. So these are things where you have a hole in a full depth structure, and that hole is such that you can't instead represent it with beam elements. So for example, that square hole in the bulkhead on the fuselage to the right. We don't have the ability to represent point-to-point beams, so sort of an arbitrary space truss where you specify the nodes and the connectivity. That would be great for something like a welded tube fuselage, on a tube and fabric aircraft, or a lot of engine mounts on general aviation and other aircraft that are basically point-to-point structures. Brian has been able to do some of that, which I'm sure he'll show, but it's not really a first-class support. And then since we don't have solid elements, we don't have the ability to look at what I would call solid structures, things like the fitting between a wing body join, like this image down here at the bottom, where you would really want to analyze, the details of the stresses around the bolt pattern and the rivet pattern. And to do that, you need solid elements, and you need to mesh that up in a three-dimensional sense. Since we don't do any solid elements, any brick elements, we can't do that. So units become a complicated issue when you do structures. As we talked a little bit yesterday, most of OpenVSP doesn't really care about units, right? It's units agnostic. Whatever, if you imagine that your model is in feet, then it's in feet. And if you imagine it's in meters or parsecs or whatever, it's in that unit. And the only time that we have to be more specific is when we do an export. For example, if you export to a CAD interchange file, then you need to tell the CAD file what you're thinking so that when it gets imported into CAD, the CAD program knows what to interpret it as. Now, the world of structures is more complex than that. The first thing is that I find that in real life in structures, a lot of times the structures team works in different units than the rest of the team. So for example, the conceptual design team, the layout people of the aircraft, they may work their model in feet, and the structures people may work in inches. Or if you're metric, the aircraft design person may well work in meters, and the structures people are then going to work in millimeters. And so you often have a conversion that's happening when you go to the FEM file. But then there's also the problem that material properties have to be put somehow into consistent units for the analysis. And this is also a challenge because it's often very hard to find the material properties in the units you need them in when you go to, the web or to a material properties database. So I find that material properties are often specified in just sort of a random soup of units. And so to take care of this, VSP has the ability under the structures menu, you tell it what are the OpenVSP model units. So this is the length unit that your entire aircraft is modeled in. And then you also tell it what units do you want to use, do your FEM solve in. So both the length and the mass units used there. Now, the consistent option here is basically a legacy, which basically says, don't convert anything. I know what I'm doing. My model units match my export units. And so that's there really for a compatibility setting, so that models created before this capability was added would still work. For most of us, even if your model is in feet and you want to export in feet, go ahead and just set the model units here to feet and set the export to feet, or whatever it is, and we'll convert by multiplying by 1. But this allows you to go through and tell it, what are the mass and what are the length units used for these definitions. When you're specifying materials, if you go and you look up some material property online, what I've found is that, as I said, you can't ever trust what units those are going to come in. And if you find 5 different materials, they're going to come in 10 different sets of units. And so we actually, if you're putting in user-defined materials, then you're actually going to specify exactly the units for each of the material properties that you use as you find them. So for example, here, the density of the material, you've got a pull down where you can tell exactly what density units it's in. And this allows you to go through and for the density, the modulus, the thermal expansion, you can specify those units as you find them, and VSP is going to take care of converting those, and we'll show you what they'll be when you export them to FEM. So we'll do that conversion for you and show you what it is. But that way, if you find your material properties in random unit soup, it'll take care of it and put all that all together. Similarly, properties. When you go in, you may want to think about your beam as you have a stringer. If you think about that hat section, that may be a standardized hat section that you look up in a handbook, and that's a 2-inch hat section. So you want to be able to specify its dimensions in those units, even if your main model is in feet, and even if you're exporting and doing your FEM analysis in meters. So you can specify all these things a little bit separately. So there's different options for user-defined materials. You can define just isotropic materials, so everything's the same in all directions. The simplest things, just like aluminum, steel, and titanium. You can specify orthotropic materials. You can specify orthotropic, but with transverse isotropy applied. That's going to be very common, I think, for a lot of what aerospace people will do. Or there's actually a laminate tool that will build up a lamination using classical lamination theory. And so you can go in and you can put in apply schedule, and we'll do the CLT calculation and calculate those laminate material properties. So there, each lamina is chosen from the material library that you have. So if you want to go in and have the latest high strength Torre composite, you'd go into the material property first and put in that as a lamina, and then you'd come over and use that and put in the ply schedule for the thicknesses and the orientation. And together you'd make that into a buildup, and then you could use that in your skin or whatever. Okay. So then properties is where we combine a set of materials with a thickness in order to make a property that then gets assigned to an element. So you choose either, you can set up these, and you might have a property, for example, for your upper wing skin property and your lower wing skin property, your forward spar and your rib property. And so they're going to be either properties for shell type elements or beam. You'll choose which material from the material set, and then if it's a beam, you choose the type and you assign its dimensions as appropriate. Okay, the first thing you do when you're building up a structure is the first tab in the structures menu is you need to choose which geometry the outer shape of the structure is going to be based on. So in this case, a pod, and then you click add structure. And so you choose which one, you add that structure, and that'll add it to this list. You can create multiple structures based on the same geometry. So for example, if you're working with a wing, it's very common that you would create the main wing structure, and then you'd come back perhaps and want to do a more detailed structure of the aileron. And so to do the aileron structure, it would also be based on the OML of the wing. And you'd come in and you'd select the OML of the wing again, create a second structure, and then go into that and use it to define to define the a second structure. This menu, if you come back to this tab and you click on whichever structure you're using, that will apply then to the rest of the tabs. Or down here at the bottom, these last sort of 4 rows on this GUI, they persist no matter which tab you're on, and so you can switch which structure you're working with down here at the bottom without having to go back to the structure tab. Okay, so the second tab is the part tab. And here, when you're working on a structure, say the wing structure, this is where you add different parts. You add the ribs, you add the spars, or whatever else it is. And so you type in the part name that you want, and you choose the type from this pull-down list. And there's a large number of types that you can use, and you click Add Part. Once you've added that part, it's added to this list. And then to really drill down, you click on Edit Part, and Edit Part will pop up, and all the parameters for that part will be displayed, including up here at the top, everything is always the same. So on a part, you can just say whether you want to keep the shell elements or delete the shell elements, and then whether you want to create beam elements. So what this does is if you have, for example, a rib on a wing, the beam elements will be created at the intersection between that rib and the wing. So that intersection curve becomes those beam elements. And so if you wanted to put something in where you only had the beam elements, so you only had those stiffeners but not the rib, you would choose to delete those shell elements but create the beam elements. And so then that's why you have these 3 options. You can either keep or delete the shell, and then you can choose to create or not create the beam elements. And then depending on whether you have shell and cap and beam elements, you choose the properties to apply for it up here. And then below that are all the parameters that exist for each different part type. You'll see that in this part list, some of them are not highlighted or are grayed out, I guess. That's because those grayed out ones only apply to wing type parent geometries. So the parameterization of ribs and spars are specific to wings, and so those parts are only available for wings. And since this is a structure on a pod, we don't see them. If we switch over and we were instead doing a structure on a wing, then these grayed out cases would come back and we would see them. So here's those common part properties that I just talked through. We have the keep, delete, shell elements, and beam elements. We associate the properties, and then we define the material orientation. So that orientation, basically, when you do a composite layout, you have to tell the FEM code what is the local 1 direction and 2 direction for that composite layout. So that tells you with your 45, 45, 90 applies, what that's measured relative to. And so that orientation, there's a lot of different choices here where you can choose, the global XYZ direction for that orientation. You can choose the component XYZ. You can choose the local part U and V direction. So if you're on a rib, that's going to be the U and V direction of that part. Or you can choose a direction based on that outer skin, the skin that you're cutting with. So that would be things like the UV direction or the RST direction. So that gives you pretty much all the control you could want on defining on a per element basis what the orientation of the material properties will be. So we have a bunch of parts that I call surface parts. These are all basically cutting surfaces that are used to slice and cut the geometry in order to build a part. We have a couple of these. We have rib array and slice array. And these are handy for specifying more than 1 rib at once. So if you want to specify a bunch of ribs that are uniformly spaced, you can do that with a rib array. And there's a nice option over here that if you set up that rib array and then you want to do some more tweaking, you can click this button, individualize, and it will automatically convert those, say, 7 ribs that you had into 7 individual ribs so that you can then go in and tweak them one at a time. The spar and rib types and also the polyspar are only available for wings, whereas the dome component is only available for things that are not wings. The polyspar is new since last year. It's a new geometry component. And what it's really good at is if you have a spar that has different breaks in plan form that as you go out the span of a wing, we used to have problems with there creating a gap in between those different portions of the spar. And so the polyspar takes care of those things. And frankly, my recommendation going forward is everybody should use polyspar for everything. And we're just going to leave spar there as a compatibility setting so that anybody who has a legacy model that uses a spar can still use it. But there's really polyspar is going to be preferred in every way going forward. So we also have the ability to do what we call subsurface parts. So just like subsurfaces in the main OpenVSP, we can define subsurfaces in structures. And we draw those subsurfaces on the OML of the component. And you can use those then to either define beam elements around the boundary of that subsurface. You can also use it to define a hole. You can say, draw something for a landing gear cutout and then delete the elements on the interior of that to create a hole in the skin for the landing gear. Or you can use it to define different structures, different material properties. So for example, you could do a subsurface to define the inboard section of the wing and then apply a thicker material property to that inboard section of the wing compared to the outboard section. Now, something I haven't talked about yet is that there's a new kind of subsurface coming to both the main OpenVSP and also structures. And that is the ability to define not just ellipses and rectangles and line type subsurfaces, but actually to define subsurfaces using any of the cross-section types in OpenVSP. And some of these may be a little bit wacky and over the top, but you can come in, for example, and you could define a 4 series airfoil cross-section type, subsurface type on your structure. You have to keep in mind that subsurfaces are interpreted in UV coordinates. So if you're doing a 4-digit airfoil, we're evaluating that 4-digit airfoil in UV coordinates and then mapping it to whatever your geometry is. So that can create strange effects, but I think you'll get the hang of how that works. Most importantly on this, if you really want flexibility, is the edit curve type works. And that edit curve type allows you to do either Bezier curves or piecewise linear curves where you can go in and really have complete control over what you're doing. So mostly, I expect that if people use this cross-section type, they're probably going to go straight to the edit curve and use that as the cross-section definition for these. There's a few special parts that are a little bit different. One is the skin is by default created, but if you wanted to create a structure that just has a frame, say it was again, a fabric-coated aircraft and you're not taking any structural credit for the fabric, you would be able to go in and still use the skin to define the OML, to cut your ribs and spars and define that shape, but then you would want to delete the skin element. So that option is there. There's also a special part called trim. So trim allows you to trim other components, but you specify, a set of ribs and spars or whatever that you would use as the boundaries of that trim, and then it will delete all the elements that pass that. So here's an example of this. The wing over here on the right, we have a spar and 2 ribs, and then I have this arrow pointing aft of the spar, inboard of the outside rib, and outboard of the inboard rib. And so where those 3 arrows are all true, we'll then cut out and trim the structure. And the result of this is the picture up on the top, where we have this mesh created with the ribs and spars all meshed, but then we've cut out this chunk here in the middle. Now, if you set this up, for example, if you define these arrows, for example, if this inboard arrow was facing towards the root and this outboard arrow was facing towards the tip, then all of those arrows being true is the empty set. And so it can be frustrating when you first set up a trim. You might end up in a situation where you have a trim and then nothing happens. And the reason for that is typically that you have the empty set. And trims are pretty easily created. They're just you choose the trim type part, and then you go in and you choose from which of your components. You can do this as many times as you want, which of your parts, I mean, and you choose which of your parts, and then you either, if the arrow is showing the wrong direction by default, then you click the button to flip the direction of that arrow and it'll show it the other way. Another special part type is what we call fixed points. So a fixed point is the ability to basically force a node in the mesh. And you can use this to assign point masses or to build up an assembly by saying, you know, here's a hard point in the wing, here's a hard point in the fuselage. We're then going to connect those together. You can also use it as a way to assign boundary conditions and loads. So if you know you've got a point load and you want to place that at a certain location, you can then put that fixed point in, and then you'll be able to find that later. Fixed points can be applied to a body, either to on the skin, on the OML, or on a part. You can place a fixed node on a rib, for example, and it's going to force that wherever that point is, that UW point, it'll force a node point in the mesh. It'll also then name that point, and it'll be written out at the top of your FEM file, and the node numbers will be consistently assigned. So if you use a bunch of fixed points, say there's 10 of them, they're always going to show up as the first 10 nodes in the FEM file, and they're always going to be numbered in a consistent way. And that's really handy, because if you do something like assigning point loads or building an assembly out of this, and you're doing some of that outside of VSP in your, say, your FEM preprocessor, that way it'll always be the same. It'll always be the same nodes, even if you change the mesh or change the structure. You can also have off-body fixed points. So those are attached to a body point, but then they're, you know, offset in space from that body. And that allows you to specify some point out in space. And this can be useful for, you know, engine mounts and other attachments, things like that, where you want to start to build up that kind of a space truss type approach. You can apply boundary conditions, and the way this works is you are constraining the degrees of freedom of particular nodes, either one node or a group of nodes. And so every node has 6 degrees of freedom, 3 translations and 3 rotations. And what we're doing then is we're really telling VSP how to choose the nodes that we're going to apply this to. So we can either apply a boundary condition to based on a part or a structure or a subsurface. So that's sort of the scope that we want to search. So we down select we down select the scope that we want to search, and then if we choose a part, we tell it which part or which subsurface we tell it. And then we tell it, what do we want to constrain? Do we want to have the user specify what's constrained, or do we want to use some of these preset ones? But you can just come in and tell it which of the 3 translations and which of the 3 rotations you want to constrain. And then, you know, if we just do a part and spar 1 and we don't do anything else, we're going to apply that boundary condition to every node on spar 1. And so down here, we can basically specify a box, and this is in the finite element model units. We specify a box that says, like in this case, we've said we want to apply it only to y less than 0.1. And so you can specify as many of these coordinates as you want. So you can specify, you know, a region in space that's applied after, you know, whichever part or subsurface or structure you've down selected from. So doing that, you can zoom in and you can tell it where you want to, where you want to apply that by BC. Okay, coming over to the next tab, the mesh tab. This is substantially similar to the way CFD mesh works in terms of specifying mesh resolution and different meshing controls. We don't use sourcing in the FEM mesh. we do everything based on the curvature-based meshing. So there's some global mesh controls on the max and mid edge length and things like that. You can either work in absolute or relative. I really recommend people work in relative. This is, even though the default is absolute. And the reason for that is, again, compatibility. Historically, we only had absolute, and so everybody's files, if you've ever done this before, have been saved with absolute. And so then when I introduced relative, and that became new, we had to leave the default at absolute. But you're probably going to get to a good mesh fastest by using the relative settings. The way this works is the maximum edge length is, when you're in relative, is a fraction of the bounding box of that component. So if you have a wing, it'll be basically driven by the wing span. So you can think of this maximum edge length as a fraction of the wing span for each edge length. The minimum edge length, when it's relative, is a fraction of the maximum edge length. So this minimum edge length, the default here is 5%, 0.05. That's probably a reasonable number for a lot of models. So what that says is that your shortest edge will be 5% of your longest edge. Likewise, the max gap is a fraction of the maximum edge length. And so the default there is 1%. So simply by turning max and min edge length to relative, you then really get down to where you're doing most of your meshing adjustment using just the maximum edge length. I'm not going to go deep in the rest of these controls. They're the same as they are on CFD meshing. There are some FEA specific options. One is we do have a quad meshing capability. It's not a good quad meshing capability, but they in fact do have 4 sides. So what we do is we take our triangle mesh and we insert a node at the center and then split that triangle into 3 quads. We have the choice of whether you work with low order or high order elements. In general, my recommendation is use high order elements across the board. The exception there is there's some solvers that just don't support them at all. And maybe I'm out of date on some of this, but Tax is a really cool solver from Georgia Tech that has an adjoint capability. Last I heard, it does not support high order elements. MyStran is a open source Nastran clone. ComLab and Nastran 95, which is an open source release of Nastran from NASA, all of those don't support high order elements. So we still have the low order element capability for them. And then you can add in a node offset. So this is done automatically for assemblies, and you probably don't need to deal with it. But basically, this just changes the node number ordering so that if you're going to take 2 files and combine them, both of them can't have node number 1. So what you would do is you would just offset one of those files to avoid that collision. But if you're doing assemblies in VSP, I take care of that for you. All right, as I said, the quad meshing, we're just taking our tris and we're splitting them into quads. I do scale the meshing parameters so that the same rules apply and the edge lengths still work. The intermediate points, both on the center of the panel and on the triangle edge, they're placed on the surface and on the curves. So we're not creating quads on a planar triangle. We're creating these on the rounded surface. The data structures that I used to do this under the hood, I changed everything to sort of fully support quads. So all the edge data structures, all the connectivity, everything works with quads. So if we ever, have support and need to go back and do a better job of, generating a higher quality quad mesh, a lot of that groundwork has been laid for doing that. This isn't just I'm not just converting it on the fly as I write triangles and subdividing each triangle in 3. Okay, once you've generated a mesh, there's a bunch of visualization and output controls on the FEM tab. So up at the top, you tell it, which files do you want to write out and, give the paths and turn that off. You can control the visualization. So this is what's shown on the screen. Here with these controls, you can choose whether to show the mesh, the nodes, and the boundary conditions, and whether you want to color it. And there's 2 options for coloring it. I think we have a picture of that here in a moment. But you can either color things by tag, which basically means by part number, or you can color it by the reason. And that's the reason is i.e. the criteria that determine the local mesh edge length. And so if you're generating a FEM mesh or a CFD mesh and you're confused about, why am I not getting clustering in this area? Or why is my mesh too small in this area? And you've been changing some of the curvature-based meshing parameters and you're changing it and you're not getting the change in the mesh that you want or that you expect, come in here and change the coloring to by reason. And then there's this key, and basically all these colors of green, blue, and red, every element will be drawn with that color, and that'll tell you which of these criteria is what's driving that local mesh edge selection. And it's really helpful for diagnosing meshing problems. The last tab on the FEA structure setup is the CAD tab. And so this is, instead of exporting a discrete triangular quad FEM mesh, this is so you can export a step or an IGES file. So we name those files up here. You can tell it how to name the surfaces. Depending on your CAD program, when you import this, if it's able to understand the names, it'll actually read in, and the thing that you called rib will show up in your CAD file as rib. And so you can basically choose how do you want that name formatted and what information do you want embedded in that output file. There's a few options down here about exactly how it gets written to CAD, and then if you do this intersection, there's some visualization, so you can come in and drill in to see what that mesh looks like. But so if you don't like our mesh, you may be able to use this as a way to, take the step file and go into something else like Patran and use the same structures definition, but use Patran as a mesher and apply your boundary conditions and everything from there. You can also output the structure without trimming it. And so that's actually done completely separately in the file export menu. And then we have the untrimmed IGES and step structures definition. So that'll pop up either these two GUIs where you choose which structure and you tell it a few options that are similar. And that'll dump out the structure without attempting to do any trimming at all. So this is beneficial if you want to go to CAD and the trimming that we're doing in VSP isn't importing properly. If there's something wrong with our trimming, if it's crashing, or if your CAD program cannot import it, then what you can do is you can instead just back up a step and you can export our cutting planes. And what you're then going to have to do is go into your post processor or your CAD program, and you'll have to do that trimming in that intersection yourself. But the hope here is that your CAD program is going to be able to carry that further if there was some problem with the import. So you also have this as a backup option to get that structure into whatever tool you're working with. And I'm already well over time for this, but it really blends into the next talk. So I'm going to just go ahead and continue with the next talk. And if we have time at the end, I'll come back and do some demo. But if I don't, I know that Brian has a lot of really great demos in the following sessions. I am going to address some of the questions right now. Andy asked about the material properties. Is there a place for inputting the references? So attributes is the answer for that. Unfortunately, right now, we haven't added all of the attributes GUIs to all of the structures entities. And so it's not immediately obvious on a lot of those things how to go and add attributes to the structures. It is all under the hood because every parm and every parm container inherently has the ability to have attributes. So you could use the global attribute editor to go and add attributes to those entities. But we don't have it just sort of one click away. That's certainly something that we can work on adding. And I think that's yeah, although, and then there is a note, independent of attributes, there is a note on each material property where you can add some stuff, and that predates attributes. So that is there for adding, typically, like you say, what's the reference of where you got this material properties data from?